Okay, let's go, Panos. Let's share your presentation.
Okay. Can you see my screen?
Yes, you can start from the start. Okay, I'm sorry. Don't rush. I think, guys. So if you are not able yet to build, it's okay. I mean, keep doing that while Panos is speaking, and if we need help, and also you have the breakout room. And if we are in distress, just reach out for having a breakout room with someone. Okay. Hey, let's go.
Okay, so I'm going to present you what you're going to be seeing for this Run Lab 2 today. The prerequisites that you need in order to run Lab 2 is to have completed the Lab 1 so that you can reuse its environment that you have already set up by now, hopefully, or until this presentation is over. You can find the tutorial for this lab here in this link. Let me just quickly post it to the chat. Rafael is going to walk you through this later on. I'm going to give you an introduction about what exactly you are going to be seeing and the developments we've been doing with respect to the CU-DU split. So in Lab 1, you've seen the G0B running as in a monolithic mode as a single process. So, and in this lab, you're going to be seeing the UE being split in two portions, the centralized unit and the distributed unit. As one of the functional splits that we have implemented in OEI, as also Florian showed in the earlier presentation. Overall, just to give you motivation for this CU-DU split procedures, the functional splits, as you know, they play a key role for 5G as they can allow for much higher flexibility, scalability, and cost-effective network deployments. It also promotes the interoperability between different vendors by promoting the usage of common interfaces between the disaggregated components. And also it makes it easier to adapt to different 5G use cases, which are aligned with different quality of service requirements. These are some of the motivations, some of the reasons why you have 5G promoting so much the functional splits. So in this presentation and in this lab, we're going to be focused in this split as defined by 3GPP in option 2, where you have the RRC and the PDCP running at the centralized unit and the rest of the run stack running on the distributed unit. More specifically, we're going to see the control plane exchanges over the F1C protocol, the F1C interface between the CU and the DU, which will support the UE end-to-end registration and PDU session establishment with the OEI core network, as well as the user plane traffic exchange over the F1U interface using the GTPU protocol. So in essence, you're going to see the same validation methods that we showed before for the monolithic G0B, but this time it will be done over the CU-DU split. A bit more of information. As I said before, the current experimental setup that we have and you are going to be seeing, it consists of a single CU and a single DU entity talking with OpenAirInterface UE. The validation that we're going to show is being done in RF simulator mode. So here, the CU entity incorporates both the control plane and the user plane in our current implementation status. As I said before, it includes the RRC and PDCP layers, and it talks with the DU, which includes the RLC, MAC, and PHY layers, as well as some RRC intelligence put in it. So it communicates over F1C and F1U for the control plane and user plane traffic, respectively. Where we want to go with respect to our developments, what is the roadmap? The roadmap is that first we want to include the E1 split between the CU-CP, the control plane, and the CU-UP, the user plane. So based on 3GPP, you can have another interface, the E1 interface, that would split the CU entity in the control plane and user plane blocks. And also, we want to be able eventually to support multiple CUs and DUs to allow more flexibility in our deployments. What exactly is the F1C functionality with respect to the control plane that we have integrated? This mainly refers to the integration of the so-called F1AP protocol messages as per 3GPP 38473 and release 15.6. The F1AP messages are in principle container messages that carry information that is exchanged between the CU and DU, and they can be grouped in 3 different categories. The F1 setup messages, which are responsible for the SCTP, they come after the SCTP association establishment as the F1 talks, the CU and DU talk over the SCTP protocol over the F1 interface, and it includes information that the CU and DU have to know about each other, like the IP that they are going to be using, the ports, etc., as well as some important configuration updates that can be carried out through the F1 setup messages, and some system information transfer messages between the DU and the CU. Then we have the F1 downlink and uplink RRC messages, which are in principle container messages that include pure RRC and NAS messages between the CU and the DU in downlink and uplink direction. And finally, we have the F1 UE context setup messages, which can support the establishment of signaling radio bearers and data radio bearers between the CU and the DU. The transfer of RRC cell group configuration updates between the DU and the CU throughout the AUE registration process, as well as the establishment of GTPU tunnels between the CU and the DU entities, which is a required step in order to enable user plane traffic over F1U. The F1C integrated functionality also includes the necessary updates in order to interface with the RRC in order to trigger the generation and the handling of F1AP messages. Now, with respect to the F1U integrated functionality in OpenAir, the F1U interface, as I said before, is using the GTPU protocol as per 3GPP 28.28.1. The OpenAirInterface has updated its implementation on the GTPU in order to support user plane traffic through both the N3 interface, the interface with the UPF and F1U interfaces concurrently, so that we can support an end-to-end traffic exchange. And this is being done by being based on separate GTPU instances for each interface. The GTPU implementation also supports appropriate tunnel management APIs for the creation, the update, and the deletion of GTPU tunnels. And the traffic is handled at the CU and the U based on different callback functions that we specify at the tunnel creation phase. And these are different for M3 and F1U interfaces in this case. That's what I mean by different. Just to give you an overview of the implementation architecture in OpenAirInterface with respect to the F1 split, the CU-DU split. So as you might know, the communication between different tasks, in other words, threads in OpenAirInterface, is mostly performed through the inter-task interface messaging queues. So one task is sending this sort of ITTI messages to another task. And here we show how the tasks which are involved in the CU-DU split interact with each other. So the F1AP CU and DU tasks interact, as you can see here, with the RRC task in order to handle the F1AP control plane messages. The GTPU task interacts with the CU and DU and RRC tasks for tunnel management API calls, as well as with the layer 1 and layer 2 task at either PDCP if we're talking about the CU, or the RLC if we're talking about the DU for the user plane traffic transfer. If you want to see more details about the description of this implemented architecture in OEI, you can refer to this document in this presentation in the slides. Regarding the code availability for the CU-DU split, there are currently 2 active branches. This one, the NRF1CF1U extensions branch, which is the one that you will be using for this lab, and you can find it in this link here. This is in a merge request, which has been there for some time now. It's almost ready to be merged, and it will be merged to develop soon. And after that, we started also working on some extensions with mostly with respect to the F1C that cover some work with respect to extending the UE context management procedures through the F1 interface, which are required in order to be more aligned with the standards and in order to be able to be in a better state in order to perform interoperability with other equipment, which is actually what we are also currently doing. We are testing and we are extending our code in order to support interoperability with the commercial CU and a commercial UE. The instructions now, you're going to see in a minute the instruction for setting up this environment in this setup in the specific powder environment. But if you want to run it on your own on a separate environment, there are instructions for 2 different types of installation. The one pointed out here is the classic bare metal installation. And there is also another possibility for direct deployment of the RAN and core network components based on Docker images and Docker Composed, thanks to Raphael, who has prepared this, where you can deploy on the fly this environment and see it running, in fact. Just to give you also the pickup trace over the F1C protocol that shows all the types of the exchanges that lead to the setup of the F1C connection between the CU-DU, initially with this exchange of setup request, response, and configuration update messages. Then you have a bunch of downlink and uplink RRC message transfer messages, as I described before, which are included in F1AP container messages that can include either RRC or NAS content. that lead to the successful PDU session establishment. And also we have the, as I said before, the UE context management procedures, which are used in order to carry RRC configuration information and information about the setting up of SRBs, DRBs, and GTPU tunnels. And you have this sort of different types, the UE context setup request response and UE context modification request response messages. And this is a slightly different trace than the one that you're going to be seeing after this presentation, as it includes the updates that I referred to with respect to the UE context management procedures. So a few words about our ongoing work and the next integration steps, although I think I have already highlighted most of them. Currently, as I said, we are doing the interoperability testing between our DU and the commercial CU from Acceleran. And this is going quite well. We can say that we have actually completed this task in the sense that we have successful PDU session establishment through this interoperability for the UE. And we can also have some user plane traffic, at least with ping. And currently we are trying to resolve some issues in order to be able to have some experiments with heavy loads of traffic with iPerf, etc. The next integration steps, as I said before, will be the integration of the E1 interface, and then at a later step, the support for more complex deployments of multiple DUs and CUs. And with this, I think that we can now start our Lab 2 session, unless there are
one question is how
yes?
synchronization is guaranteed between CU and DU?
Synchronization. There is no specific message as far as I know for the...
Well, yeah, maybe I can help. So it is, control plane is SCTP. So SCTP, it is like TCP. It is serial, the order of the bytes is committed by the protocol itself.
Yes,
then in F1AP, there is a protocol defined by the 2GPP saying that the DU sends a setup request, the CU answers to the setup requests, and so on.
Yes.
Okay.
Any other questions?
Well, one last question is: can you share your presentation on the Slack? You have a
yes,
a share button, so people can retrieve it.
Yes, I can share it on the chat. Yes.
Je m'entends quand je parle. Okay. Let's you can stop sharing, and I will start sharing myself.
Okay.
Okay, let me share my screen. Share. Okay, share. You should see my nice VM I have. Okay, so here is the Git repository that the Polar team put in place for all the labs. So one of the labs was the lab 1 that we did. I thought that we could have some time, or for the one that are in advance, you have an extension where you can run. I will just show it. I will not execute it. You can run with a noisy channel, and as I mentioned in the chat, you can add this telnet server, and then you restart the GNodeB the same way, and you add some more options for the UE, and you are able to modify the channel. So normally, I think I took some picture. Yeah. So compared to the the NR scope that you just did before, where you are having perfect IQ samples here, you do start to see noise here on the PBCH, on the broadcast channel, and also on the PDSCH. And if I go, okay, I open a telnet server, I am able to modify the channel model and change that with -5 dB, and I should have a more noisy look, especially on the broadcast channel here. So if you have time or during our dinner break, for us, you can continue your experiment and so on. So let's go on the lab 2 hands-on session. First of all, one question I did answer on the chat, but to get this nice T-Shark that, for example, Panos shared, you have to use a very recent T-Shark or Wireshark with 5G support, and in that case, it's 3.4.8, and I have said how to install that. I mean, you will get this nice new version that are supporting 5G compared to very old Wireshark versions. Okay, so normally you should stop the core and you should clean up your workspace. So I don't know if we will have time to finish up. We have half an hour. Yeah, I think that's right. When are we stopping? At 8 or at 8:30? Oh, so I have 1 hour. So we can do it properly together. Okay, so Panos did share the PowerPoint on the chat. If you want, you just turn on it. Okay, so so I'm using the SSH method because I'm a lazy person. I want to copy paste. So I have my 4 terminals that you guys have, and I type bash everywhere. So this is an experiment I started a few hours before the workshop. So first of all, I need to create again my building environment. I will if you are already built or you are done, you can do that. Otherwise, you can wait a bit to finish your experiment. So here, with doing this git clean command, let me just maybe increase the font for you guys to see. Yes, it's better. Git clean will clean up your workspace, and so it will remove all the build artifacts that you have used for, especially in target run build. Okay. So we will switch to the branch that Panos talked about, the NR F1C F1U extension branch. Since we clone with a very shallow workspace, we need to fetch the branch with a depth of 1. So again, so I keep it this one. And I check out to the branch. Okay, let me just look like this. And normally, if I do a git log, I am on Panos' latest commit that was December 2nd, where he merged develop into NR F1C F1U extension branch. The rest remain the same. So we copy again I'm going to do the CMake target repository folder, and I will build again same thing from scratch. Okay, so let's go.
Maybe it's too late, but if people are late, it's not really necessary to remove everything. You can rebuild on the existing files, and CMake will build only the necessary ones.
Yeah. I'm just preparing my environment for the rest. So it's still building. What is another stage? Yeah, so you need to, Rodolphe, you need to do this git fetch command. I did that. You only need to do that. If you don't do that directly without doing the fetch command, it will not run. Okay. Okay, and to get the lab instruction, I just pasted it. Okay. Can we have access to that after? I have a question for you, Kirk and Cobus. How long can these people use their experiment? Can they, for example, use it over the break that we will do later on?
Yeah, no, definitely. They can, you know, we'll leave it active. I originally said till the end of the week. I mean, we can leave the project active for, you know, till the end of next week, so people can come in later and do it if there are resources available. And certainly the ones they have allocated, the experiments they have running, they can just keep using for the time being. So yep, they can definitely do that.
Yeah, so for example, yeah, Kirk answered that the default duration is 15 hours if you didn't do okay. Bagarwal, you need to change to go to CMake is not found. That means that your build OAI minus capital I didn't succeed properly. Yeah, and as Kirk said, that you can start from scratch again later. Don't turn it now. Okay. Yes. If let's go back to the lab 1 instructions. Yeah, so some people were, so just to explain the difference, the build OAI minus I, and you can here specify with USRP or what, this command has to be done once in the life of your server, because you don't need to reinstall the packages and USG driver or any SDR like for Lime. You just need to do that once in the life of, and as Laurent said, that you can, this build OAI and CMake and Ninja will do the trick, even if you are switching branch. Normally, you should be able to distinguish the objects that are need to be recompiled from the one that should not be recompiled. Yes. So here, Vikash, I think if you don't have CMake, is because your build OAI minus capital I didn't work at all. Yeah. Yeah. Let me switch back to if. Okay. So here, okay. And if I do yeah. So you see. So for example, for the G0B, currently we are at almost 8,000 files to be compiled. Okay. So if your build OAI minus capital I fail, you can't do it again. It will reinstall from scratch package that didn't install properly. And you need to be in the CMake target repository to execute that command. Normally should be okay. And what I have seen is on, so why I did we did this branch or this tag with the powder name is I saw that one package was difficult to install. So that is very important if you are running the build OAI minus I, that you do build from this tag and not any kind of develop or that. And okay, and I think we should be done soon. Yes. Okay. Okay, let me go back to the lab 2. So till now, pretty much what we did is we just switched branch from the develop branch to the NR F1C F1U extension branch, and we rebuilt not only the GNodeB but the NRUE and the NR scope. Okay. Let's for me start the core. No, so to answer on Laurent's comment is no, I wanted to showcase what I discussed in my presentation, that we could specify which version of USRP. Obviously, in these 2 labs, we don't care about having USRP build. Okay. Okay, the build is done. I have started the core. So let's start. So here I will do that and be very careful, okay? Because otherwise your pickup will be very, very huge, okay? So it's okay. So I'm gonna start the CU. So CU is the one that is connected to the core and does not require to have any kind of SDR connected to it. So I remove the -D that is a scope on that one, because anyway, it's not on the physical channel. Okay. Okay. Normally, the CU did connect Docker logs -F on the AMF. Yes, it did. Okay. And here I changed the name, so you can see that I did change the name of the component. It's really the CU and not the monolithic GNodeB that we ran before. Okay. Next, so I need another shell now, again, still from CMake targets folder. So let's go over there. Yeah, I think it should be okay. So here I'm starting the DU with the same command as I started. Okay, is there a lot of command? Okay, -O stands for configuration file. Okay, so either you can provide a lot of options when running any soft modem at OVI, but the -O will specify a configuration file. And just for you to look at it, I'm gonna just do a cat on it. And here you have a lot of options that you need to modify if you want to change them. But here we are specifying, for example, the frequency band, so 78, the number of PRBs, so 106, and the spacing, that was the numerology that we saw on the UE. So all of you see, not all of these options are available at the command line, but you can run all of them. Oops, copy. No, I forgot. Okay, copy. Yeah, way too long. I have the question. Yeah, too many options. Yeah. Okay, I'm starting the DU, and normally I should see. Okay, normally I should have the NR scope coming from Remy is not fast enough for answer. Okay, let me copy the okay, I have my scope. Okay, I have my GNodeB scope. Okay, so let's start now the UE. And normally, the UI should be connected to the core. Okay. Okay, no camel. I think it's also again some options that were very old and legacy. So before I joined OAI, it was 3 years ago. On the LTE, you were having to load a kernel module to insert traffic to the PCPD layer. I don't remember, and that was very complex. And I don't remember. I think it was François from Nokia that did propose to use tunnel, and that was much easier to use. So it's to not use the old method, and in fact, the old method is not even supported anymore. I think, especially on the 5G core or on the 5G UI. So here I have the UI that is connected. I have the scope that is blinking. And I have a nice consolidation on the PBCH and on the PDSCH. And if I do the training up to the end, if I do a ping, oops, should work. I have the ping. And if I look at my T-Shark -R TMP test, you should see the trace that Panos showed about. So the SCTP initialization, then the first F1 AP messages between the CU and the DU, then the GNOB, what you were talking about, the SCTP heartbeats. Thank you. And then we have the UI attachment, and here we have the pings on the F1U. Okay, on port 2153. And that's it for the lab 2. So I think you can continue yourself. Okay, so for the GTP to see GTPU, I think I need to change the port to. Okay. When you run, you have an assertion.
Rodolphe found his error.
Okay, perfect. Perfect. Okay. So what I will do is I will use the same terminal, same setup to insert noise on the UI side, just to show what I did also. So I will stop the UI. I will stop the ETU. I will stop the. Sorry. Yeah, I'm not able to join a breakout room yet, but yeah, okay. So Laurent is helping you, or Laurent, can you have a breakout room with Luis? Okay. So
yes, sure. I don't know how to do that.
Don't worry, Camille will invite you to a breakout room with Luis.
Okay. But, yeah.
Okay, so I will just add the telnet server, so I can add noise, even in this CUDU environment. Okay, so it's quite fast, and normally I should see the telnet server shared libraries. So, and here I just need the option. Okay, normally I have edited the UI. So yes, I have already done these steps of copying this file to the local repository etc and editing the UE file. So you need to add the channel model configuration for adding noise. Okay, so I already did these 2 commands. Okay, so I will restart, in fact, the CU and the DU as I did before. I didn't change anything. Let me start the DU. And I will add some option on my UE. So I enabling the channel model on the RF simulator, and I'm also starting the telnet server on the UE side. So here we will add noise on the downlinks only. No, not on the uplink. So normally, if I look at, let's see if I get the. Okay. On the G node B, should not have changed. I should still have a perfect constellation, as I can see. And let's wait for the UE. Is the UE coming? Yes. And normally now you can see that I have noise, both on the PBCH little green square and on the PDSCH, compared to the scope we showed with the perfect IQ samples. And normally, if I do the telnet command and I I'm looking at the current value of the channel model. So currently, the noise is at -10 dB. You can see that you have other parameters with the Doppler, the path loss, and the offset. Remember, that will be the question at the end. And I will modify here just the noise level to -5 dB. And if I go back to my UE scope, you see that at the PBCH, it's way worse than before. I think that's it for me. You have this library. It's because you did not run with the --RF sim option. So I will stop my experiment. Okay. I will kill it. And I will do a sudo kill all tshark. So, okay. Okay, the PDS, I think you need to, the PDSCH logs. Is this on the, okay, that's it. Yeah, so I will answer order of question. I mean, the RF thing is going as fast as your computer can run. So it's not real time. So hence why we have the latency, and also when you are running hyperf, it's depending on your hardware. So for us, RFSIM is more a developer environment for people that has no access to a SDR. They can still develop the new features running on with RFSIM. Yeah, so that means that it doesn't run as fast as a real time. Okay.
I'm back with Luis. I don't know if there was a question for me.
No, it's okay. I'm good.
Luis machine, for some reason, the system disk is full. I don't know why, in fact.
Okay.
You will reinstall, and if there is the same problem, it's more a question for Polder team than for me.
Yeah, so I think the machine are allocated with 16 gigabytes of file disk, and that's
yes, it's what I saw, but it's probably the same for everybody.
Yeah, this could be due to this is Dustin from Powder. This could be due to maybe attempting the install in multiple directories somehow. I don't think there may not be enough room for 2 different installs, so that's a possibility. I'm not sure else.
Oh yeah, I confirm. I mean, I tried that with Docker and didn't work at all. So you can only have one build.
Yeah, it is certainly possible to ask for more space when you use these resources on Powder, but we just used the default here because it was good enough for one build.
Well, Luis said that he will restart with a new machine, probably succeed.
Okay,
that should work. Also, you don't necessarily have to restart your experiment. You can also reload the node. This is an option that you'll see under that in the list view. If you push that little gear icon on the right, you'll see an option to reload the node.
Let me stop sharing. Okay. Why is it? So I guess if I go to my experiment, on this one,
actually it's the top one, so you have to check the box, and then there's a reload option, and that will just start from scratch, but it will be the same experiment.
Okay. So if you guys have a problem, I mean, just you reload your node, maybe it will and restart from scratch.
So just to be clear, it will reinstall the operating systems. You'll have to redo everything. If you just do a reboot, whatever you installed will still be there. So those are 2 separate commands.
Running DU, exit, say no configuration file in the file. You may have a typo on your, or you are missing maybe the minus capital O option. VJ has a problem of F1AP critically reject. Stop sharing. Oh, it seems that I made a typo. No, it was a typo. Okay, okay, it's a typo. It was, you have to use a minus capital O and not a 0. Okay, sorry. And for VJ, it's after the U handle G node B.
For VJ, we can try to debug together.
Okay.
It's
breakout room, VJ and Laurent.
Okay, let's try.
So VJ, Laurent is coming at your help in a breakout room. So let me just reshare my screen. So if you have difficulty typing your command compared to like I did, so local bin, no, repository bin, and you have a start CU. Local repository bin du, no, start du, enter. And if I start my UI again with noise, that would be working. Yes, for Sergio, maybe also you have the same problem, -O, or if you can type the local repository bin and start UI, NRUI. You should type U for you everything. Yeah. So certainly, okay, yeah, you certainly used the wrong executable. Okay, guys, thank you very much. If you have questions, I mean, now, yeah, if you have, okay, Dragoslav. Okay, I saw that. I saw in the UI code that several different devices, USRP, Iris, or Proto are supported. Internet. That is something that. So if you want to use USRP or Iris, then you are not in RF simulator mode. You will be with SDR because USRP, Iris, or all of these are SDR components. So you won't use RF simulator. Once you start using RF simulator, that means that you are using to use Ethernet. I think there were old modes certainly that were still supported, at least in the LTE. But I will say that currently the only one that we do support is RFSIM for transporting the IQ sample between the G0B and the NRUE. I think that's in the plan. I think currently the GU is still monolithic. I would say monolithic, but I think we will split the DU with the RU. I think, is that correct? Or Panos?
I mean, that's a different split. I think that there is some implementation for the split between the DU and RU. I mean, you can consider
it's more like okay, it's more like the
monolithic
ORAN 7.2 or something like that.
Yes, yes, yes.
So for example, I think we do support the ORAN 7.2.
Yes, that's what
I mean RU split.
Yes.
I don't know.
What kind of GTPU?
No, I'm looking at on the chat. There's the question.
Yeah.
If I'm getting the GTPU, can it be rectified? Are you on the correct branch? Because I'm thinking that you may be on the first branch that we used for the lab one, Bagarwal. Okay, so you're on lab 2 branch. It's kind of associated. Just looking at my okay. I think maybe Cobus or Kirk, if you want to show demos of what you guys, I mean, we can do it. I mean, while I might go to do a breakout room with this person.
I think that'd be great, Dustin. Do you still have your demos?
I can barely hear you.
Yeah, Cobus, we can't quite hear you, but I think you said, yeah, that's great.
Sorry,
You can go through one of
My mic was on top of my head.
Yeah.
Yeah, if you still have your demos, I think that'd be great. And yeah, if you can maybe just tell people about expiries and extensions as well, that'd be great.
Yeah. I'll mention that first. Let me share my screen really quick. Again. Okay, so is that visible?
Yes.
Okay, great. So for people who may want to go back through the instructions later, retry things for both labs 1 and 2, it's possible to extend your experiment on Powder. It's pretty easy to get to this if you just fold down the top green tab on your experiment and push the extend button. You'll have a range that you can extend by, and maybe 1 or 2 days should be sufficient here for you guys. But you also need to enter something that explains what you're doing, why you need to extend the experiment. So something like OAI workshop continued use or something like that would be fine. And then push the request extension button, and someone from Powder will, if the extension doesn't just go through automatically, someone from Powder will come along and approve it.
Yes,
okay,
for short extensions, it's auto approved, but for longer ones, it kicks it to an admin.
Right. So, well, I guess I should go. It's been a moment here. Let me go back to the slides here really quick. So, so what we did in those first 2 labs was to run all of these network processes on a single compute node with an RF simulator, and you can actually transition relatively easily to using real hardware on Powder. And so I'll just run through these slides really quick about Powder profiles and how they work. These are resource recipes. They say what resources you're going to use and how they should be set up, and then they get instantiated into experiments. The lab profile that you've seen was really simple. It was just a single node, and there's a node type. This is a part of a profile script with a particular image that included some requirements. You can instantiate profiles by searching for them after you start an experiment, and one of the options for profiles with real hardware that is similar to what we did, but includes real hardware, is this OAI RF bench profile. This, rather than using a single compute node, includes 4 separate nodes, one with that will play the role of a Docker host, one that will play the role of the Gnode B compute, Gnode B SDR, which is an X310, and then the UE SDR and UE compute. So this profile is different in that it has some parameters different than the single node profile. So you can select the compute type for the core network, or the compute that will be paired with the SDRs for running the soft modems. You can also, for example, specify specific hashes of the OAI RAN or the core network that you want to use. Additionally, you could use a different image if you wanted to instantiate the compute for the SDRs. So this paired radio workbench profile looks like this. In a little more detail, we have near edge compute with 3 different hosts. Like I said, one for the Dockerized OAI 5G core, one for the Gnode B, one for the UE. That's all on near edge compute, and then 10 gig interfaces into the NI SDRs, and these have wired RF, so coax cables with 30 dB attenuators on the TXR export and RX2 ports going between the devices, and they share a common reference, 10 megahertz reference in pulse per second via an octa-clock. In terms of what you might do in a profile that would be different than this single node experiment or profile that we started with is, well, you'd request more nodes. So in this case, this is the profile for that paired RF or paired radio workbench profile, and we're requesting a PC for the core network, requesting a network interface and setting an IP on it. And then we're running a deploy script that will deploy the core network. Similarly, for the G node B, in the same script, we're specifying another compute node, specifying a particular image for it, and connecting it to the interface on the core at the core network, and then once again deploying OAI. And this deployment script will deploy core network, G node B, or NRUE, depending on what the role of the node is, and it uses some external scripts to do that. And of course, we have to connect these compute nodes to the actual radios, and this is another node in Powder parlance, and this includes an ID that is in a list somewhere else in the script that identifies a particular X310 in this case, and the same for the UE side. So I won't go over that. You've already seen this picture. This is the X310s that are in this the paired radio workbench. With that, I'll just go to the experiment that I have running for that. So let me get back out of the that single node experiment and see I have several experiments running here. One of them is this 5G demo bench experiment based on that OAI RF bench profile. So I'll click into that. You can see our core network connected to the G node B compute, G node B SDR, and then the NRUE compute and the NRUE SDR. And if you go to the list view, you can see how to, if you've already provided SSH keys on your Powder account, you can SSH into these nodes directly. This I instantiated a while ago, and all of the startup scripts that provision the nodes have finished. So I'll go to a terminal here. Okay, so at the top, I've SSH'd into the core network node that is this Docker host, and this is going to look similar to the deployment that we've seen before. So I'll just start a T-Shark instance, and in this case, I'm going to use copy and paste since we're not in that web-based shell. Actually, I'll just deploy this first, I think. So this is the command that you've seen a few times now. It'll spin up the core network. And we'll start this T-Shark process in another session on the same node and watch some of the traffic for those core network functions. Rather than recording this and going back to the look of the file, we'll just print it out live. And once again, we'll follow the logs for the AMF. So bottom left here, I have a session on the G node B compute. We have instructions in the profile for all these commands, by the way. And there's a link to the profile, and if there's not a link to the profile in the lab instructions, we'll add it to our slides somewhere that we've already shared, that we will share with you guys. But so here's the command for starting the soft modem. In this case, we're not providing that RF simulator mode command. There's a slightly different configuration here for real hardware, but we're still providing this standalone flag, and we're not gonna run the soft scope in this case. So we start that up, and we see ng setup request and response messages between the. Oh, okay. So sometimes there's a bug with interaction with UHD, which is the driver for using these National Instruments software-defined radios. But if we just start this again, it should work. Okay, good. And eventually this this log here, the AMF log, should show that GNode B is connected. In the bottom right terminal over here, I have a connection to the UE. There's this again a long command to run the UE with some parameters we haven't seen before, which are setting some TX and RX gains. So we'll run that. And now the NRUE looks like it probably is going to hit that same UHD error, but if we just start it again, it'll work. Okay. So at this point, the UE is registered on the network. We have some hard ground statistics getting printed out at the GNode B side, and then on the UE side, I'll just generate some traffic here. For some reason, with this particular branch, I have to create a route for the interface that is, getting created by the, I'm not sure what's happening there. That's getting created by the soft node on this OAI tune underscore UE1. So I'll create this this route. Well, maybe. And then we can ping using that interface, that external data network container that's in this the OAI 5G core network with ping OAI tune UE1 and the IP address. IP address of that again is 192.168.70.135. And you start to see some traffic up here in the T-Shark log with the ICMP requests and replies. Well, it looks like we had a little glitch there, but yeah. So that's about it. This is just an example of quickly moving to real hardware in the Powder platform. And of course, the next step would be, well, potentially indoor over the air, and then ultimately outdoor over the air, depending on the desired use case. Okay, I'm going back to the chat here. Okay, it looks like most of these are answered, and okay, I'm not sure if the OAI RF bench profile can be used with this under the same project, because I'm not sure it has access to real hardware at this point. But as Kovas mentioned earlier, if you have interest in using Powder post the workshop, you can start a project of your own and get access to that hardware. So are there any other questions?
Maybe long. Your USRPs are all on the same 10 megahertz clock? Or?
Yeah, that's right. Well, in the case of the paired radio workbench, yeah, they're sharing the same octoclock 10 megahertz impulse per second reference.
So the frequency is perfect.
Right.
I think we are reaching the end of the. Okay, so.
And there is still 97 people. Huh?
Yeah, and okay. So let's go. Bye bye. See you later.
All right. See you later. Thanks, everybody.